want you to draw a roller coaster hill, like so. Okay, we're going to just kind of draw. I want you to have a high point, and I want you to have a low point, like so. Now, today we're going to be talking primarily about a transition. Okay, we're going to be talking about an energy transition. So if we're talking, if you're going to write down a big idea for today, the big idea would be an energy transition. And if you guys on the floor, you need to be paying attention. Okay. All right, so here we have our hill. Okay, we're going to look at a car as it moves down the hill in 4 different spots. All right, so we're going to imagine that we have a car on this roller coaster. Okay, we're going to call this spot A. We're going to imagine the car at spot B. We're going to imagine the car at spot C, and we're going to go ahead and imagine the car down here at the very bottom. We're going to call that spot D. Okay, so we're starting at the top and working our way down, 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 down. Okay, looking at energy. Looking at energy transitions. So A, B, C, D. Now, let's make a prediction about what we think will occur to the car. Okay? Charlotte.
Well, I think there's some gravitational potential energy.
Okay, so you think there's some GPE, some gravitational potential energy. Okay. Where do you think that's going to be the greatest, Charlotte?
Right between A and B.
Okay, you think it's going to be the greatest? Between A and B. All right. What else do we know? Predict what you think is going to happen as the car goes down the hill. Izzy. Okay, so it's going to pick up kinetic energy. We're going to come back and evaluate these predictions when we're done. Okay. What else about this car? And let's think real life here. What's going to happen to the car? Yeah. Hannah.
It's going to get faster.
It's going to get faster.
Move at a faster speed.
It's going to move at a faster speed as we go from A to D. All right. What is one of the best parts about a roller coaster, right? You go click, 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 and you start to go down. What is one of the things what's one of the best parts about a roller coaster? Yeah. Yeah, there's an adrenaline rush there. But is it like floating in space? No, it's not like floating in space. But so if we're talking about a roller coaster, what do we feel when we're on a roller coaster? Charlotte?
Going really fast and moving a lot.
How do you know, though? What are you moving through? What do you feel flowing through your hair, right? Olivia?
Sometimes it feels like you're pushing down.
Oh, that is true. It does feel like you're pushing down or you're floating up, depending on the type of roller coaster. But there's something else, yeah.
You can feel the wind.
You can feel the wind. So there's going to be some wind involved, okay? There's going to be some wind involved, and that wind's going to play an important factor in our discussion at the very end. Okay, so let's go back for a second to our roller coaster here. A, B, C, D. Now, you guys today are going to practice drawing some energy bar graphs. Okay, I'm going to show you what one of those energy bar graphs are going to look like. You're going to draw 4 of them. You're going to draw one for A, you're going to draw one for B, you're going to draw one for C, you're going to draw one for D. Okay, so I want you to, somewhere on your paper, at least half a sheet of paper, I want you to divide your paper into 4s, like so. We're going to have 4 of these bar graphs. Okay. Actually, let's do this. We're going to have a P for potential, a K for kinetic, a T for thermal, And over here, we're going to put total. And we're going to do that for all four. P, K, T, total. P, K, T, and total. P, K, T, total. So we're going to spend some time really looking at and predicting and kind of thinking about what's happening here. Okay, this is going to be for A. This is going to be for B. This is going to be for C. And this is going to be for D. All right. Now, let's think about a tall roller coaster like the one in the very first page here, like this. We're working with three types of energy. We're working with thermal, which we're going to talk about later, but we're working with gravitational potential and kinetic. Okay? I want to just kind of refresh your memory for 1 second. You don't need to write down, oh, bummer. You don't need to write down this page right here, but I want to just ask you guys this question to kind of make sure that you understand fully what we're talking about. GPE is entirely dependent on what thing? Henry? Height. Absolutely. It's dependent upon height. Okay? What is kinetic energy dependent upon? Yes. Speed. Or velocity. So in this particular case, we'll just look at it as a speed. Okay. More gravitational potential energy means that the object has to be what? Izzy? What do you think? More gravitational potential energy, the object has to be what?
Higher up.
That's right, higher up. And if we want more kinetic energy, Allie? More kinetic energy than what? It has to be faster. Very good. Trust your instincts, folks. You're doing good. So, let's talk about these different locations. Let's think and use some common sense. When you're at the very top of a roller coaster, okay, when you're at the very, very top, are you moving fast?
No.
Okay, so let's just make a few notes on our page. We have low speed. What about our height? Henry? We're as high as we're going to get. So it's low speed, and we are very high up. And notice, because I've not given you any numbers, this is about the best way to describe it. Okay? Now, what's going to happen as the car moves down the hill? Okay, Katie, real quick. What do you think? Have you ever been on a roller coaster? Okay. As you start at the top, and as you go down the hill, what happens to your speed? Oh, yeah. Okay, so we have a low speed. We're going to speed up. But in doing so, what happens to our height, Charlotte?
It gets lower, so there's less gravitational potential energy, and then by the time you get to
You're
speed, then there's barely any.
That is very good. Okay, so we are very high up. We are definitely not as high up, so we are lower than A. And that's what I'm going to put for right now. We are lower than A, and Charlotte, you're right on. Yep. It's going to definitely direct that gravitational potential energy. When we get to C, folks, when we get to C, what's happened to our speed, Addison? Oh, yeah, we're going fast. I'm going to just like fast with all caps and an exclamation point because we got to emphasize fast. I mean, you got to even say it fast, because if you say it slow, you give the wrong impression. Fast, 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 fast. Yeah. No. Mm-mm. No. You guys go ahead and go back to your seat now. Yep. No, go back. We'll let the other class finish taping and stuff. I know. Go ahead and take a seat. All right, not bad. We're going fast, but last, Abigail, what has happened to our height?
Way lower.
Yeah, we are low with all caps. So we're fast, but we're low. We're fast and low. It's different than being slow but high. Okay? We are fast and low. Now, last but not least, D. What can you tell me about D, Hannah?
We are going to have a lot of kinetic energy and pretty much zero GPE.
All right, so I'm actually just going to write it that way. We are going to have a lot of kinetic energy, and you said no or low or zero GPE. And you would be correct. All right, so we've kind of worked through this. I know from our discussion just now, you have a good understanding of how this transfer of energy. Is the gravitational energy just disappearing? Jacob Stir?
No, it's being turned into kinetic energy.
That's exactly right. And it's very important you understand exactly what he just said. It's not disappearing. It's not leaving. It's being converted. It's being changed. It's being transitioned into kinetic energy. So in theory here, we start with a set amount of energy. Okay? And in theory, it's the same energy the whole time. It's like you eat a hamburger. Okay? That hamburger has a set amount of energy. Do you know what we call that energy in the food world?
Chemicals.
Not chemicals, but it does start with a C, Olivia. Do you know? No, but protein definitely is good for us. Jacob? Calories. How many of you have seen calories on the food? People are talking about calories all the time. It's like on all the food labels. Okay, calories represent energy. So food has a set amount of energy. Now, when you eat that burger, take a big old hunkin' bite of it, right? And you just gobble the whole thing up. When you eat that burger, does it stay the burger all the way through and it comes out as a burger? No. That'd be painful, be bad, okay? What does your body do with all of those calories, all that energy? It absorbs it. Some of it gets used, right? Some of it gets used so that I can, quick feet. Some of it used so that I can talk really loud or talk really soft. Some of it used so I can pump my arms or pump my blood or breathe. No punches, okay? Oh, you said hug. I think you said punch.
I said punch first.
Oh, okay. So that energy gets repurposed. That energy comes from our food. This is the same idea. We start with energy, but it's like a burger. As the object moves, it takes that energy and it uses it in a different way. It's using that energy to get faster, but in the process, it's decreasing in one category and increasing in another. Mrs. Biebrick?
Is there more kinetic energy at D than D? No.
There is more kinetic energy and less gravitational potential energy.
Which D?
At D than B. D here would be the fastest. So let's go to our graphs. We'll go to our graphs, and then we'll pick it up from there. Charlotte, question.
Are there multiple kinds of kinetic energy? Is there like gravitational kinetic energy, or is it all one same type of?
It's all one. If something's moving, it has kinetic energy. Now, things move for different reasons. So some things, it's always due to a force, right? So we move because maybe our blood's moving because our heart is pushing it, okay, and then pulling it. Or maybe we're moving because we're pressing off the ground. or we fall because gravity is pulling us down. But there's always something that's going to cause the movement. However, okay, everything is in motion, and all that motion is just summed up as kinetic energy. Okay?
Like chemical energy, is that a kind of potential energy?
It is a kind of potential energy, yep. And that's what food kind of has in it. Yes.
I think I just noticed it, but you have food in here.
I do have food in here. That's true. All right. Let's take a look at potential, gravitational potential, kinetic. Thermal we'll get to a little bit later, okay? And let's just look at it as if there was no thermal energy. We'll just look at it gravitational and kinetic. All right, so how would I draw my bar graph in A? Jacob. Okay. Potential energy all the way up. Kinetic energy, none. So if I have a total, what would that total have to be? Charlotte?
Well, I was going to say, wouldn't there be a tiny bit of kinetic energy because you're still sort of going up? Or if you were to take a freeze frame, are you saying like...
We're freeze framing it. Yep. We're saying if the car starts from rest, there's absolutely no motion to begin with. Now, on a roller coaster, the car is always moving just a little bit. You're right. Okay. So there would be, in a real situation, that kinetic energy bar would be a sliver. A sliver. All right. What would my total look like here? What's my total going to look like here? Gavin?
Exactly.
That's exactly right. It's going to be exactly the same height as the potential. Absolutely.
I don't really get total. Like
Total energy? It's how much energy you have to work with. It's like money. So I have a set balance in my wallet. Okay? I can't spend more than that, and I'm not going to take in more. All right? So it's the same idea here. I have a balance. All of my energies have to add up to that balance.
Okay, so if you have one all the way up, like if potential energy is all the way up, then you can't have anything else but then...
That's correct.
Okay, so...
Yep. So the only way to get kinetic or thermal is to pull from potential.
Okay, because it's just being transferred.
It's just being transferred. That's exactly right. That's exactly right. All right, now in B, think back to our roller coaster. Look on your paper. Okay, we've got our roller coaster. What has happened? Jacob Stir. We've gone down the hill. So we've seen what happened here. Abigail? The potential's dropping, and what's going up at the same rate? The kinetic energy goes up. All right? So however much this drops, that's how much kinetic goes up. We're drawing this without numbers, so we can kind of make it up. But we should kind of think about our roller coaster for a second, okay? Is there going to be a lot of kinetic at B?
Not so much.
No. Half? Is it halfway down the hill? No. So it's got to be less than half. That's important. So let's go ahead and kind of draw potential being down a little bit. Okay, so it went down about that much. On my screen, it's about an inch and a half. And we're going to raise kinetic up a little bit. So about that same amount. And does the total change?
No.
The total does not change.
Is it always going to be like that? Like the same height?
If we assume that all the energy gets converted, then yep, the total should not change.
If there's thermal energy?
Well, thermal energy is a little bit tricky, which is why we're saving it for the very end. Yes.
So you're always going to have a total of that much. You're always going to feel all that energy.
That's correct.
You can't not have it.
Well, that's right. There's no such thing as no energy. You're always going to have some energy, and that energy just moves back and forth between. So I don't want to get ahead of myself, okay? But there's a way that we'll look at this even in greater detail. probably tomorrow or next week. So we have this potential converting into kinetic, but the total is not going anywhere. So it's just shifting. How we see this change? It's going down, height decreasing, but Ruth, it's getting faster. Okay, so C. Okay, our potential energy at C, should it be at half or less than half? What do you think, Hannah?
I think it would probably be less than that.
I think you're right. Actually, yeah. So if half is about that high, then our potential energy is going to be just a little bit below it. Maybe not even that high. I might be a little too generous there. As a result, what's going to happen to our kinetic energy bar? Okay, Olivia. Yeah, it's going to go up. Okay, so it's going to be considerably higher this time around. That's right. Well, on a roller coaster, you speed up pretty quick, don't you? All right, so we have potential, we have kinetic. What's our total going to look like? It's going to be the same. The total energy really does not change. We're just shifting energies inside our roller coaster. Charlotte.
So, like, B and C are kind of like the same distance from the top and from the bottom. Like, C is about the same distance from the bottom as D is from the top. So it's kind of just flipping to...
That's right. Now, it won't always be that way, but I did draw it kind of with that intention, yes. All right, the last one. The last one. What do we think here? Hannah?
Well, there is going to be pretty much zero potential energy.
Zero potential, because we're at the very bottom.
Pretty much, if you look at A, the potential energy bar up that high, do that for the kinetic energy.
All right, I can do that.
That basically just goes to the top of my head. Oh, did we get your trash on yet? No.
All right. All right, so we've looked at how the energy is moving in our roller coaster. We're looking at how it's transitioning, how it's being converted. Ladies and gentlemen, energy cannot be created or destroyed. Can't be. The amount of energy you start with is always the amount of energy you have. It's just how it gets used. Some of it gets used over here to heat things up. Some of it gets used over here to move things. Some of it gets stored away as potential. Maybe it's because we've lifted an object up. Or maybe it's stored away in a chemical bond. Or maybe it's stored away in an elastic band. If I stretch a band, what's it going to do when I let go? It's going to snap back. That's very similar to this. You had potential, and as that rubber band snaps back, it's moving, and then it stops. There's potential again. So all of these different scenarios, everything that we're doing every single day, there's always a total amount of energy in the universe. But that energy is constantly flowing. What is the biggest source of energy for planet Earth? For planet Earth, Addison? The sun. We get a tremendous amount of energy from the sun. Okay? The equivalent of hundreds of nuclear weapons every day. So where does all that energy go? Does the planet burn up into oblivion? Do we turn into a pile of dust? Are we dust? We are, technically.
Yes, we are.
Jacob, sir?
They go in the object.
That is exactly right. It gets used. So who's going to use most of the energy from the sun? Okay, what's going to use most of the energy from the sun? Hannah, do you know? We do, but then there's something we eat, and there's lots of it, and it's green, and it's all over the planet. Plants. Plants use energy from the sun to make food. They consume tremendous amounts of energy. The sun heats our planet. Okay, weather, wind, all of those things are the product of a heating Earth. Okay, so we absorb and use that energy from the sun. Where's the sun getting the energy? From all these little nuclear reactions. Okay, they're happening, quadrillions of them, every day. Okay? Yes?
Doesn't it, like, go through, like, all the elements in the
When a star dies, it can go through many of them. It can go through many of them. But you'll learn more about that in chemistry. Okay? Yeah.
Like a supernova. Specifically, would you call the sun's energy specifically? Would you call it, like, nuclear?
It'd be nuclear energy. Solar energy produced by nuclear reactions. Yep.
Okay, so also, could you, since the planet's soaking it all up,
Mm-hmm.
would you be able to transfer that energy? I mean, would it still be nuclear energy? Could you be able to get nuclear energy out of it?
Well, no. When the sun releases the energy out, the energy comes out in the form of heat waves. It comes out in the form of basically different types of radiation. And then we absorb that radiation in different ways. But plants will take that energy and do exactly what this roller coaster is doing, is converting it. What plants do is they make sugar. And then they use that as food to grow tall and create their leaves, and then they store it away and they create bigger stems, and that's how plants grow. So it's all about the conversion process. Plants don't do this in any magical way. They literally take elements and they kind of put them together and they store it away as chemical potential energy. So yeah, it's a fascinating process, right? But it's really important. If I could stress one thing to you, one thing I would never want you to say is that energy just leaves or is destroyed or just goes away. We have energy, and it just gets moved around. Okay? It doesn't go anywhere. Now, we're almost out of time. Thermal energy is tricky. Thermal energy is tricky for a couple of reasons. Okay, thermal energy is known as heat energy. So all of you put your pencils down for a second. Okay? We're going to create some heat energy. Put your hands together. Rub. Okay, pause. What is this? What's creating the heat? Okay? Friction. All right, let's describe friction in its simplest sense. What is my hand made out of? Henry? Let's go even deeper. What's my hand made out of? John? Let's go even deeper. What's my hand made out of? Jordan? It's made out of skin. That's true. Let's go even deeper. Abigail? Let's go even deeper. It goes way smaller. Izzy? Atoms. Our hand is made out of atoms. This hand's made out of atoms. When atoms collide, okay, which is what's happening here, heat is produced. When you're going down a roller coaster, are you colliding with atoms?
Yes.
You are. Where are those atoms?
Are they in the air?
They're in the air. Every time you collide with an atom of air, what happens to that? And I shouldn't say an atom of air. Air is made of nitrogen, oxygen, carbon dioxide, water vapor, tiny little trace elements of the noble gases, etc. Air is a composition of different air products off the periodic table. But let's just say that we'll talk about air as just something, okay? When you combine or collide with oxygen, carbon dioxide, nitrogen, etc., do those particles, what happens to those particles? John? Do they just stop and they go through you? Like when I'm moving through this room, what's happening to that air? Oh. It's moving around you. Hang on, stop. Think about this. You are moving. You are colliding with air. That air has to move. Where's the air getting the energy to move? Because remember, that energy to move, that kinetic energy, has to come from somewhere, Mr. Kistler. Mr. Kistler, where's that air getting the energy to move?
I don't know.
What's colliding with it? No. I am. If I hit the air, that air is going to take some energy from me.
You get from like the food and stuff.
Gets from the sun, right. So let's think about this. Did I just lose energy? Okay, if I transferred energy to the air particles to move them out of the way, that's called thermal energy. So when a roller coaster is going down the hill, it's got to push air out of the way. To push the air out of the way, it's got to take that energy a little bit, a tiny bit, a fraction of the energy from the roller coaster. So you can hands down for a second. As the roller coaster gets faster, it's going to push more air with more force. That's why you feel the wind speed up past you. So as thermal energy builds up a little bit, and it gets a little bit taller and a little bit taller, okay, we have to add that thermal energy to our system. So I'm just going to add it up here. So it's going to increase the amount of total energy a little bit because we have to account for all that energy from all of those collisions. Does that make sense? If you're going to move something, you've got to use energy to do it. If you're going to move even air out of the way, then you have to account for that energy. All right, that's the last thing for today. It's 9/11 plus. Tomorrow, the roller coaster will be done. We will measure the actual mass of the car. We will calculate its potential, and we will use that information to figure out how fast it's going when it gets to the bottom.
I think it's going to be going 5 miles.
Ladies and gentlemen, you are dismissed. Have a good day.
How fast is 5 miles an hour?